In this lecture we are going to discuss the governing equation. We will try to derive the governing equations using control volume approach. So, what we are discussing is the fundamental physics that happens when a fluid is flowing. Essentially, the equations which are derived in thermodynamics and fluid mechanics is what we are going to use here, and we will use the control volume approach for deriving the fundamental laws, which is conservation of mass to conservation of energy, then essentially the second law of motion, the momentum conservation. So, before we start this, should understand what is a field or what is a 2D flow or a 3D flow, what dimensionality of the flow. So, your velocity v is a function of x, y, z and t. So, if I have a fluid flow in space, my velocity here is depending on the location of the fluid particle and the time at which you are measuring the velocity. Likewise, the other properties, pressure, temperature, density, everything would be some function of x, y, z and t. It need not be the same function, it can be a different function, it is a different function. Now, if it is a function of just two variables, two dimension and time, then this is a two-dimensional unsteady flow. If the time dependency is absent, then this is a 2D steady flow. And if your velocity or any of those properties is just a function of some direction, some and time, then this is a 1D, one dimensional unsteady flow. So, a fluid particle that moves from here to some other location, the velocity also changes due to the movement of the particle from point 1 to point 2 as well as the time at which it. So, if I have a property that is associated with the particle that moves from point 1 to 2, then the rate of change of that property as we move along with the particle is something called the total derivative or the material derivative or the substantial derivative of that property. Okay. So, it is the rate of change of that property if you move along with that particle. So, from point 1 to 2, some property n changes from 1 to 2 and this n depends on Okay. So, if your n depends on n depends on x, y, z and t, then your total derivative, which is denoted by the capital D, is partial dn by dt plus dt plus dou n by dou y plus dou y by dou t plus dou n by dou z into dou z by dou t, which is dou n by dou t plus u into dou n by dou x plus v into dou n by dou y plus w into dou n by dou z, where your velocity vector has components u, v and w in the x, y and z direction. Okay. So, if I rewrite that, vectorially I can write it like this, okay, where del is dou by dou x I plus dou by dou y j plus dou by dou z k in the Cartesian coordinates. Okay. So, that is the expansion of your material derivative. Now, let us look at what exactly it means. So, your dn by dt is a combination of two terms. One is the unsteady component, meaning the property that changes from time t to time t plus delta t. Okay. So, n is a function of time also. So, this n that is measured at some location is going to change, or it will be different at if you measure it at a different point of time. Okay. That is this part dn by dt. Second, the second term on the right hand side is something called a convective component, or convective change of the changes of n due to the convection of the particle. So, if I measure the property n at location 1 and I measure the property at location 2 at the same instant of time, then there will be a difference, because f or n is a function of x, y, z, s, or the property is a function on space. It is going to be different in space. So, at the same instant of time you are measuring n, and that difference, because the particle is going to move from point 1 to 2 and you are moving along with the particle, you feel a difference in property n, and that is due to this particular term, which is V dot grad of n. So, n can be any property. Okay. Now, we are going to evaluate this property or this derivative, the rate of change of property n for a given control volume. So, let us look at what is a control volume. Okay. If I have a fluid flow, I consider a mass at time t which occupies a volume which I define it as my control volume. So, this consists of several particles which contribute to the mass of the control volume. Now, I consider at a different point of time what happened to the mass that is inside this particular control volume. So, this control volume changes to this particular volume at a time t plus delta t. The particles that is constituting or contributing to the mass is carried to this particular volume. So, the volume might have changed, the mass is the same mass, okay, or the particles are the same particles. If you have a difficulty in imagining this arbitrary shaped volume, consider a divergent pipe. Okay. So, you have a volume here. So, this would be a circular shaped. So, this is my control volume at time t. After some time, at time say t plus t1, time t2, I have a different control volume. Okay. So, the mass that is associated with the particles inside this control volume is the same. So, the mass has carried, but the control volume has changed. Now, we are going to look at a time where this delta t is small, which means so if this delta t is small, my arbitrary control volume would have moved to a distance in such a way that there is an overlap of region. Okay. So, if delta t is very small, this control volume would have moved a little bit and that will overlap with the other volume. Okay. If you look at this way, my control volume here at time t is now moved to this time t plus delta t. Okay. So, essentially I have region 1 and an overlap region 2 and the new region 3. Here again 1 overlap region 2, 3. So, associated with this mass there is a property n. Okay. So, it depends on the mass of the fluid that we are considering. So, it is an extensive property. Okay. So, an extensive property. Okay. Now, I define introduce a new variable eta, which is property n per unit mass, okay, or the density of the property n. So, if this is my control volume or in a given mass, your n is now defined as integral eta dV d volume. Okay. Weierstrass is okay, where rho is the density of the fluid. Okay. So, essentially eta into dm and density into volume is your dm, and this is integrated over the volume. Our aim is to find the total derivative dN by dt. The rate of change of this property when it moves from time t to time t plus delta t, what is the rate of change of that particular property. Okay. Now, from the fundamental calculus, I can define dN by dt to be limit delta t tending to 0 n at t plus delta t minus n at t divided by delta t. Okay. Now, n at t plus t is limit delta t tending to 0 n at t plus delta t. So, at t plus delta t, your volume is region 2 and 3 at time t plus delta t. Volume 1 and 2 is at time t. Okay. So, your property n with this definition, control volume, no integral over the volume eta rho dV for the region 2 plus eta rho dV for the region 3 minus same thing for region 1 plus for the region 2. Divided by delta t. So, I rewrite that limit delta t dN by dt. So, this is at t plus delta t, this is at t. So, I take region 2 integral over the control volume eta rho dV at t plus delta t minus integral volume eta rho dV at t. Okay, these are triple integrals, plus limit delta t, this is for region 2, this is for region 2, plus the region 3, integral eta rho dV, integral, this is at region 3 at time t plus delta t, minus limit delta t, integral eta rho dV for region 1 at time t. So, the first part, limit delta t, this, so the first term, limit delta t tending to 0, integral eta rho dV at t plus delta t minus integral eta rho dV at t by delta t, that is by delta t, this is the definition of differential dou by dou t of this quantity, which is integral eta rho dV. Okay, and these are triple integrals. So, you could write this as okay. So, this is n, which is dou by dou t of n. So, this term is the unsteady part of the material derivative of n. Okay. Now, we look at what happens to the other two terms. So, our aim is to evaluate these two terms. Okay. So, let us take the arbitrary surface we have already taken, take a small area. Okay. The normal to the area is in this direction and the velocity vector is in some other direction. Volume of fluid that is coming out of this area, small area dA, is V dot n into dA. Or simply V dot dA vector. Okay. The mass that is coming out, so the unit of this is meter cube per second, the volume flow rate that is coming out of this. So, the mass that is coming out of the small area dA is just this quantity multiplied by your density. So, this would be kg per second. So, if that is the mass that is coming out of A, then incremental quantity of N through the area dA is this quantity, which is the dm, which is the mass, into eta, which is defined as the quantity per mass. Okay. So, the total N through the entire surface, entire surface is the integral of, so the double integral over the full control surface into this quantity eta rho dot dA. Okay, in this is per second. So, in delta t time, total N through the surface is this quantity multiplied by delta t. Now, this, if you look at the control volume and the volume that is moved at delta t time, we can relate this to the following. So, I have a control volume at time t, then I have the volume at time t plus delta t. So, there is a property that is here in 1 and there is a property that is here at 3. Okay. So, the quantity of the total property N that is going through the surface at delta t time is this, what you see here, and that is precisely what you have written here. So, if I take the material derivative is the change of fluid property that has happened when the fluid moves from one to from this volume to this volume at t and t plus delta t. So, this quantity what you have written here, the total property N that is moved out of this control volume is this. Likewise, the fluid property that is moving into the control volume is this, what you have written here. So, this is this quantity. So, essentially, so the integral Cs eta rho v dot dA delta t is the flux of property N through the control volume, through the control surface. Okay. So, if it is region 3, and this is eta rho V dot dA delta T is the flux of n through region 3. This is region 1, eta rho V dot dA into delta T is the flux of n through 1 in delta T time, or the net flux is the flux out minus flux in, which is integral 3 eta rho V dot dA dt delta T minus or simply integral around the control volume rho B dot dA in delta T time. So, the second and third term in the right hand side of the original equation is now equated to the net flux that is happening. So, your dA by dN by dt, the material derivative of property n is dou by dou t, your triple integral, which is the volume integral eta rho dV, which is this particular term which we have written originally, plus the net flux term, which is this, the property n that is getting out minus property n that is getting in, which is triple integral Cs eta rho V dot dA, or simply we can replace this as eta rho V dot n dot into dA. So, this is your unsteady part of your property change, and this is your convective part. Okay. And this equation is typically known as the Reynolds transport equation, because you are trying to find the transport of the property n. N is given by this equation, dN by dt equals these two terms. Okay. And this equation is Reynolds transport